James, do you know what is the strongest material in the universe?
Hari, that's a good question. Tell me.
Okay, right. So for those of you who don't know, this is Wolverine, and the strongest material in the universe is adamantium. And that's the material that makes up his claws that you can see here. And adamantium is strong and indestructible. Well, all of you understand what strong and indestructible means, but how do we quantify that in an engineering parlance? So maybe if you can point out, James, the next slide. And right, so we want to define the engineering equivalent of what strength and indestructibility means. So if you think of a simple rod of a metal and you apply a force on it, what the material's response gives out a stress. And stress is basically the force, external force applied by the cross-sectional area, right? And it also, when you pull on it, it elongates by a certain extent. And the strain is defined by the change in length divided by the original length. So fairly simple concepts to understand, but this has enormous implications on the material mechanical properties. So as you can see here, it is a representative stress strain diagram. And if you have an adamantium, which Wolverine has, if you can pull on it, it keeps, it keeps going on forever. The slope of that line is basically something called as the elastic modulus. Now, if you see this red couple of balls on the right, you'll notice that as you keep pulling on a material, eventually it might fail at a very, very high strength. Now, real materials are seldom that way, like adamantium. You have a lot of flaws in them, and flaws and defects in them. What happens is at a certain stage, these flaws become activated and you start getting something called as a plasticity. We'll talk about that in great detail, but this is the general introduction to the idea of strength and strain and why this is important. One of the important things to keep in mind, of course, is that the notion of a theoretical strength, that you could approach this very high strength in materials when there are no flaws present in them.
So that you can have a theoretical material like adamantium, which fails at very high stresses, which is related to the force, or a more realistic type material in the blue, where you have defects, which then weaken the material.
Absolutely, yeah.
Okay, and so how is this related then to real materials, and why is small-scale mechanics? So when I say small-scale mechanics, I mean nano-microscale mechanics of materials. So as Hari showed on that last slide, this crystal lattice is a combination of atoms arranged into an ordered structure. And therefore, to understand the properties of the material, then we actually need to be able to understand the material from this electronic and atomic length scale and move all the way through the microstructure of the material to the bulk scale material properties at the millimeter length scales, like we might have for Wolverine's claws. So to actually really understand and to be able to then design advanced materials for new applications, we really need to have a very good understanding of the material behavior at all of these length scales, or across these length scales. And so how do we do this actually at the small scale? So bulk material testing, as is shown here for a piece of copper, which is being pulled along its tensile axis. We have a very large piece of equipment. We have maybe a copper rod, which is some millimeters or centimeters in diameter. And effectively, we grip that copper rod and we pull, or squish it as well, but we apply some sort of controlled deformation to this. And then we can observe with our own eyes, actually, how this rod starts to thin a little bit and then finally fracture. So as mentioned, materials are made up from these atomic scale building blocks. So we need to be able to take those concepts from bulk scale materials and then microscopically shrink them down and then study them at small length scales. So the way that we do this in the group is to use what's called electron microscopy. So these are two examples of electron microscopes where we can bypass these wavelength constrictions of light and use electrons which have much smaller wavelengths so that we can see materials at much, much smaller length scales. And we have two critical pieces of equipment here that maybe Hari, I think, will describe in a little bit more detail in terms of how we actually do our tests.
Right. So one of the things, like James pointed out, we can do this macroscopic testing, and we want to miniaturize the sample. So that means the first thing that you do is to fabricate it. So how do you fabricate it? You use a focused ion beam to fabricate it. Now, if you can run the video, as you can see there, we use gallium ions to shape miniature pillars or structures equivalent to what we would do in a bulk scale. So once we have that, we can see what we can do with them. So if you, right. Before that, I think since many of you are may not be familiar with the focused ion beam, I must just point out that it is very similar to a scanning electron microscope. You have a gallium reservoir to which you apply the very small needle to which you apply a very high electric field. So the gallium becomes ionized and it moves towards your sample. Now, gallium is much more massive. Therefore, you use electrostatic lenses to basically focus them and hit your sample. At the source, you can get a resolution of 5 nanometers with the tungsten needle and so on. But because these are massive ions and you cannot use electromagnetic lenses to focus them, you have electrostatic lenses. You typically get a sputtering resolution of the order of 50 nanometers. And as you can see, yeah, sorry, James.
Sorry, and because these are much heavier
absolutely, yeah,
ions compared to electron, for example, that means you can remove material through
absolutely.
sputtering.
Right, yeah. Of course, you can sputter them and shape materials like we saw in the previous video. What is nice about this technique is that we can use that for very soft materials like magnesium. This is an example of a fancy geometry which is just used for shear testing. And on the other hand, this one is a very hard material. And we can even shape that to make cantilevers and use them for fracture testing and so on. So the diversity is immense.
Okay, and then the testing, Hari, could you explain a little bit about how, so once we manufacture these geometries using FIB, how do we test them?
Right, so we have what is called, of course, we have our SEM, which we saw before, and you can see here, there's basically tools, miniaturized tools, which you can use to probe these samples. So you can think of them, they're basically nano indenters. As you can see here, it's usually a diamond tool which presses onto the surface, and you can observe what's happening in the video. If you go ahead, this is a sort of a picture of a in-situ nano indenter. This one is a Hizitron Bruker PI-88. So it's a very simple machine in some sense. We have a probe, which is basically made out of diamonds, which is the one that you saw in the video, which is connected to an actuation system. I'll come to that. On the other side, we have basically a sample holding stage, which also functions as a resistive heater so that you can heat the sample up. And these are paraphernalia for cooling and so on. And we also have a motorized stage which allows the samples to move to find your location and so on. So the actuation comes in two parts, typically two varieties, I should say. One is called as a load actuation. So you can use an electromagnet to force the shaft to move into the sample. You have lateral springs with which you can, it is for support stiffness and to measure the load. You have a capacitance sensor which can measure the displacement. So these are things that they come in very handy. Now there's another kind of actuation which is called as a displacement actuation. This uses a piezoelectric material. You apply an electric current to that and you get a displacement. And that actuation is used to apply, for example, displacements and loads onto the sample, right? So this here is an example of a test done inside our PI-88, where we have a micropillar which we fabricated with FIB, and then this is I think it's a ferrite iron pillar tested by Ms. Chunhua. And what we can notice is that we can correlate the load displacement curves. So you can see at some point there's a deviation from linearity and there are load drops. You can correlate to things that we see visually with the microscope. So it comes in very handy later on.
Okay, so what we're seeing here basically is inside an electron image of when we do this deformation, and then we can collect this load and displacement information in real time.
Absolutely.
Okay, and then we can actually take some of the really nice experiments that Hari and his colleagues do within the electron microscopes, and we can compare this to what we might have for some common engineering type materials. So these are examples now from really large scale bulk testing again, but you see that you have a similar type of relationship between the stress and the strain that we see on the small scales compared to what we see on the bulk scale. So we're really able to effectively miniaturize these tests. And what you could notice here is that we have at the top, so this is at higher strengths, so higher stresses, advanced steel type materials. And then we actually have a huge amount of play in terms of our material properties. So our elastic modulus, as Hari explained before, but also our strengths and our ductility by changing the material, of course. So aluminium is a softer material than steel. And we see that, of course, in the bulk scale stress strain curve. And so what we want to do then is take those fundamental features of stress strain diagrams and also analyze those features or characteristics at those small scales. And so what we can do is we can take a simplified stress strain diagram, and we can break this up into 3 separate features or characteristics that will explain in a little bit more detail how these relate to small scale mechanics. So the first one, of course, is that when we take a piece of material and we start to apply some strain or deformation to this material, we have this linear response in terms of the stress.
Right.
So Hari, why do we have a linear response, and how can we measure this actually at the small scale?
That's a great question. One of the important things about elasticity is also that it's reversible. Maybe we didn't mention that. The moment you remove the load, it goes back. So the analog is very nice. Let's say these things can be thought of as, atoms can be thought of as small springs that are connected. And when you apply a force on them, the spring stretches. If you're taking a plate with a spring, you pull on it, it stretches, and you leave it, it goes back. So that's very reversible in nature. Now, the property which governs this is called the elastic modulus. Now, that relates to what is called as the spring constant. So you would remember from your high school that if you have a force displacement curve that relates linearly with respect to this force constant. And therefore, if you take this analog forward, you get a linear response. So that explains your question. So how do we measure that? We think of these as springs. So again, we use our nanometer tool. You have a sharp tip and poke the surface of the specimen. What you get is, as you record the load displacement curve, we can use the unloading stiffness, meaning that you poke into the surface and then slowly retract it. As the material the probe retracts, the material pushes back on the probe, and you get an unloading response. You can use this unloading stiffness related to the contact area, and this is a constant relating to the geometry. You can extract out an elastic modulus from this. So why is elastic modulus important? It comes in a lot of engineering application, but then this is my favorite example, that of adamantium. So we come back to Wolverine. Adamantium would not work on a human bone. Why? Because you put a piece of adamantium, let's say somebody fractured their hand, you want to put in a rod there. What adamantium would do is it'll take away all the load that is applied onto the bone. And for your bone to heal, it needs to have a small but healthy amount of load. If the adamantium takes away all your load, your bone doesn't get a chance to heal and it atrophies away, which is why you need materials which have similar modulus or moduli to the bone. And one commercial candidate is titanium or alloys of titaniums, which have very close matching with the modulus of the bone. Yeah.
Okay, so using these techniques, then we could really do very localized measurements throughout a material structure to see how the elastic modulus changes, which might have importance for applications, Hari.
Right, absolutely.
Okay, great. So then, okay, let's take that analog of a spring, and we take our 2 atoms connected by a spring, and we stretch through this elastic regime here, but now we keep on stretching. What our analog would tell us is that at a certain point we'd keep stretching, would follow this red curve, and then at a certain point our spring would break. But that's actually not what we really see in reality, because we see, as mentioned before, something responsible like this blue curve, so that at a certain stress level that we start getting another mechanism which starts to dominate. Yeah. And that mechanism is plasticity. And so what is plasticity? We can think about this in a very simple way, as mentioned. So this is exactly a schematic of what I was talking about. So if we take this lattice structure, so a perfect crystal lattice, and we apply a stress to it, in this case it's a shear stress to the material, Then at a certain point, these springs will become overburdened and they'll break, and then you'll form new bonds on that, let's say, slip plane of the crystal structure. If we think about this now in terms of how the geometry of this lattice would relate to the strength of the lattice, let's say the theoretical strength, then we would have a relationship like the one here. So a very simple relationship between the normalized strength and the lattice geometry, as that is basically just how far apart these atoms are spaced on their slip plane. Now, reality, of course, it's often different, as we saw before in the stress-strain curve. So if we look at a number of different materials, so let's say from diamond up here to copper or aluminium down below, then we see actually the strength of those materials diverge significantly from our theoretical strengths. And why is this? So why do we get some materials, all materials basically, which diverge from that theoretical strength? And the answer is because we have defects within real structures. So we never have really a perfect crystalline lattice, but we have something a little bit more like this, so that we have some defects within that crystal structure. And maybe you can imagine that it's much easier to move those defects through the structure than it is to continuously be breaking bonds across that slip plane.
Yeah.
So therefore, the energy barrier for moving these dislocations or defects, which is called plasticity, is much lower when we have these defects within the structure.
Right. I can think of an analog, James, here. So anybody who has pulled a heavy rug will know that sliding it is really hard. And you can do it easily by creating a small ripple and moving that ripple across. And you would find that much easier to move that heavy carpet or rug when you make that little ripple and move.
So kind of flicking the rug and
absolutely.
Having a wave within the...
Absolutely. And the analog to a 1D defect is almost identical in this case.
So it's very, very difficult to pull a rug on especially on a flat surface.
Right.
Yeah. And so why do we see then these differences actually in terms of when we go back from rugs to crystal structures?
Right.
And as mentioned, this is because of the geometry. So we see this relationship between the strength and the geometry, and that for harder materials, that is to say materials like diamond or silicon, we have a much more compact lattice along these slip planes, which means that the atoms are pushed closer together, and it's much more difficult to squish or to slide those relative planes of atoms. So maybe it's in your analog, Hari, it's maybe like having an elephant sitting on your carpet, and makes it even more difficult to kind of move.
Good one.
But on the other end of the spectrum, we have what's called face and a cubic type lattice structures like copper or aluminium, which are not as compact. So we have much broader geometries. And these allow a much easier or lower energy barrier to pushing defects through the crystal structure. And so therefore we see a strength which is much, much below the theoretical strength. We can kind of see that here as well if we take this schematic. So we have a covalent and compact crystal lattice like for diamond or silicon. You could imagine that to move this defect or this dislocation along this plane is much harder than we might have for copper, where the dislocation is in a much more wide region of the lattice and the energy barrier for moving this is much lower. But we're talking also about nano and micromechanics of materials. Right. So is there any influence actually of the size when it comes to this, or is it only just the lattice considerations?
That is a very good question, James. So typically when we have materials like silicon and diamond, as you showed very nicely, that it is already approaching the theoretical strength, right? The strengths even at bulk scale approach the theoretical strength. So there's a very small, limited influence of the size. But when you have a material like copper, which you showed right now, in the bulk scale, it is very soft and ductile. But as you keep reducing the size of the sample, what you start noticing is that the strength of the material actually goes up. And this is related again to the fact that in the bulk material, we have a lot of dislocations which can easily move. But then as we keep reducing the sample dimension, what we notice is that in a tiny volume, it's less probable that you'd find a defect. So you may have to either create it or move a defect which is probably stuck somewhere. So reducing the size, what it does is basically makes your strength higher. And the other thing that you can notice from a curve like this is when you reduce the size of the sample, the dispersion in the data actually goes up. And that is again related to this probabilistic or stochastic event where the pillar that you shape may not have a defect that is mobile or easy to move. So it becomes very probabilistic and
so
hence
statistical at this stage.
Absolutely.
And what do these dislocations look like then, Hari? Is there a way of also kind of characterizing and playing around with single dislocations?
Yeah, so that's a great question. Dislocations leave a signature. As you pointed out very nicely, that's an elastic strain signature. That is, in the localized region of a defect, you always have this bonds that are stretched. And you can use a transmission electron microscope. And when the electron beam falls on the sample, these localized strain fields sort of, you could say that, take you away from ideal diffraction conditions. And you see these things as dark bands or curved regions. So these are, in effect, the dislocations that you see them by their strain signature. Now, it's nice that we can actually observe as we pull on a little metal piece of sample, you can see these things moving under the influence of stress. If you look at the picture here on the right, during deformation, the dislocations are curved, but if you remove the stress, they come back and become straight. Now, this again relates to this very nice schematic here. You can see that under the influence of a stress, the dislocation tends to curve, and you can correlate frame by frame the dislocations and measure their curvature and use that to calculate the instantaneous stress that the dislocation is. So in effect, you know what the dislocation is experiencing for it to move through the crystal.
So we've basically established that dislocations mediate then this plastic deformation type behavior, or at least defects in crystal structures do. Right. But then my thoughts are then, how important is this? And one way that I like to kind of imagine this is to take, let's say, something like this, a cube of engineering material, which is maybe slightly bigger than a sugar cube. And as we've discussed, that we have defects or dislocations as well within these engineering materials. And so if we take all those dislocations and we connect them end on end in this tiny little cube of material, we actually find that that chain of dislocations would reach from the surface of the Earth to the surface of the Sun, which is approximately 147 million kilometers, which is a significant distance actually to cover. So even in this very small amount of material, we have a huge amount of these linear 1D defects, which are in the material, which are controlling then the strength response of that material. So dislocations are critical, but one thing that is also critical is the structure of materials, in particular metals. So we discussed a little bit before about microstructure, but maybe we can delve back into this a little bit. And so if we think about applied materials, maybe one that most people would have seen are galvanized steel railings, where you see this interesting sort of pattern. And basically all of these different contrasted regions representative of different grains within a structure. And I'll explain what that is in a minute. So that means that we have these boundaries, so two-dimensional boundaries, which separate different regions of material. And this is something ubiquitous to all materials. So when we move away from a simple sort of single crystal type material, like we've been looking at experimentally, to a real polycrystal type material, the importance of these boundaries becomes really significant. This is also a micrograph of a piece of polycrystalline copper, where we see also these differences in the boundaries. The copper, of course, is super important based on its conductivities for things like electronic applications. So if you look at a specific region, so one of these, let's say, grains in the polycrystalline copper, and we zoomed in with a transmission electron microscope, what we would see is that the crystal lattice is oriented in a particular way. If we then went to a different grain and did the same thing, what we would see is there is some difference in the orientation of the atomic structure. And so what this means is that if we take grain A and grain B, and we put them together, is that we actually form, we don't have this direct continuity between the crystal structures, but we have this sort of discontinuity, which is called a grain boundary. And like with 1D defects like dislocations, 2D defects like grain boundaries are also incredibly important for the mechanical response of these of engineering materials and all materials. And so one way that we can look at this is that we can think about having a material. So we're taking a piece of polycrystalline material now. Let's say it's copper. We know now that polycrystalline copper will have a number of these different grains in the structure. So they all have their different orientations. The copper will also, as we know, have a number of dislocations within the structure. So if we stretch on this, we know from the TEM measurements that we get, we propagate our dislocations within the structure during plasticity. But what happens when these dislocations meet the 2D planar defects like grain boundaries? What happens? And this is a really big open question in material science, is whether these grain boundaries act as obstacles to dislocation motion, whether there's some degree of transmission so the dislocations can pass through after paying a small energy tax, or whether these grain boundaries act as sinks or sources so that they either absorb or emit dislocations from there. But my question for Hari now is, can we study this in a rational way?
Right. Thanks, Tim, for that. That's very nice explanation. The way we do it is this dislocation grain boundary interaction is very critical, and it depends on the nature of the grain boundary itself. Now, one way of systematically studying it is we can grow crystals with a specific grain boundary. This is a piece of copper, and we use 2 seed crystals and allow the crystals to grow, and they naturally abut each other and give you a very specific grain boundary. So you could have different orientations on either side, but then you come up with a very special boundary. Now, how do you study this boundary? Of course, we've spoken at length about FIB techniques and micromechanics techniques. So we can take the FIB and then make these micro pillars on grain A and also use that on grain B. And we can, of course, because the FIB is also a scanning electron microscope, you can actually look at the boundary and you can make the pillars, which encompasses the boundary as well. Now, we can test all of these independently and try to see if that has any influence on the mechanical properties. Now, when we do that, for these kind of special boundaries called the twin boundaries, what is found is typically the strengths of, say, a grain A and B are more or less similar, but the strength of the pillars with the interface is actually marginally higher. Now, this comes about because we have to do a great deal of experiments to resolve this. For example, our colleagues have done something like 130 pillars to distinguish this very small difference in the strength. But what really happens? So this is one interface. You get a marginal increment with one interface. But then, does it happen in other materials? Can we control it? This is another example of silver, nano twin silver. That is, we take these twin boundaries and then we use thin film methods to deposit multiple twinned interfaces, right? And we can control the spacing of the twins by just annealing the sample so they grow. So in a single sample, you could have small twin spacings or large twin spacing, which basically correlates to having a different amount of interfaces. Now, yes, sorry.
So it's similar. So here for the copper, there's just one boundary.
Absolutely.
And in this silver, then you have thousands.
Yeah.
And so what happens to the mechanics actually?
Yeah, and we can control that with annealing. We can control that. For example, when we have very few twin boundaries, you get smaller strengths. And then when you keep testing them with higher and higher number of twin boundaries, you see that the strengths actually go pretty high. So you get about factor of 5 multiplication when you change the twin spacing from 1 micron to about like 20 nanometers. So you're increasing the number of interfaces, which adds up. So one interface gives you a certain delta increment. You multiply the interfaces, and you get it's a cumulative effect of these interfaces. So
you can really control then the resulting properties of materials by engineering, in effect, the boundaries which exist within them.
Absolutely, yeah, perfect.
Fantastic. So we're nearly at the end of our journey along the stress-strain curve. And there's just one last point. So, we've touched upon elasticity and plasticity, but at a certain point, everything's got to come undone, And that happens in materials through fracture. And so what we saw from pulling on copper is that we have a very ductile fracture, something like you might see here. So that means the material is ductile. It means that we have a lot of plasticity. This leads to some necking and then a very rough ductile fracture surface. However, when we think about stronger materials, we don't always have ductile failure. Actually, we can go through where we have more brittle failure, and in particular for strong materials, like perhaps adamantium, we would stretch springs, and at a certain point, actually the material would just crack and fail and break, and that's what is called a brittle failure of the material. And this makes, of course, a big loud noise when you have a big brittle failure. And so what we can imagine then is that we have a connection to the energy of the system in the failure of the material. And this is indeed exactly what we see. So if you look at force displacement, which as we know is the analog now of stress strain for ductile and brittle materials, what we see is that the work, or the mechanical work, is the integrated area under the curve, or the area under the curve, which is equal to the force multiplied by the displacement. And this is, in effect, an energy of the system, the mechanical work. And so what is clearly obvious is that if we go from a ductile system to a brittle system where the material has failed in a brittle manner at roughly around the same force, then of course the mechanical work gone in before or to fracture is much, much lower. So it requires a lower energy in order to fracture the material. So what costs energy then in material systems? So as we've discussed, stretching our springs during elastic deformation costs energy. Plastic deformation and dissipation costs energy as well, meaning moving dislocations through a material. This has a distinct energy cost. But here in fracture, we also need to consider the creation of new surfaces. So if we look at this example of the brittle material, we've gone from a continuous piece of material to the formation of two new surfaces. The formation of new surfaces also has an energy cost. So energy is a particularly important concept when we think about material failure, as well as some of the deformation mechanisms that we've touched upon before. And why is this important? Well, because fracture has a huge cost in society. So we can talk about the billions of euros that fracture costs the economies of the world every year through failed parts or bridges or larger structures, but all the way through to a cost of life, in effect. So a lot of plane crashes, for example, a lot of their root causes are down to fracture. So therefore, it's really critical that we understand fracture and we can design against this on an engineering way. So how was this done, Harry?
Right. So you very nicely showed that when you pull on a sample, it could undergo a brittle fracture or a ductile fracture, and the area under the curve is related to the work that is dissipated. Now, this is called as a toughness in engineering parlance. But when we do this for like uniaxial specimens, that the ones that you showed, the results sometimes tend to be qualitative. Now, in order to mechanistically understand this, the way we do it is we introduce a sharp notch and then subject it to again straining or stress. So this is a nice example of a photoelastic material where you have a notch, and you can see that when you pull on this material at the localized region, you have the lines tend to concentrate, which indicates that the stress is much higher locally. And so basically, fracture toughness is the mechanics parameter that governs crack growth resistance. And you can think of this as something that bridges the global applied stress to crack field conditions. So higher the fracture toughness K, greater is the resistance for failure. So for example, you can use this and study this in our engineering materials. For example, this is an example of what is called as a hafnium, niobium, tantalum, zirconium carbide, fancy. But what it shows, if you run the video, is that, can you run it for me, James? Yeah. So if you see that, you see as we load it inside the nanometer, you see a boom, a catastrophic failure at some point. And the load displacement signature that we've been talking about here is very similar to what we get in a brittle material. You don't get any plasticity. It just goes at a certain level and then goes boom. Now, of course, this is of academic interest, but can we make things with improved toughnesses when we have only brittle materials at our disposal? So we can take inspiration from nature, which is very, very clever. What it does is basically takes so this is an example of nacre, a seashell. And when you subject it to fracture, it doesn't go straight and bang like the cantilever that we showed here, but then the fracture path is very curved and tortuous. And this is related to the fact that nature very cleverly uses organics and hard minerals to create more and more interfaces at which these cracks can diverge. So these interfaces tend to improve fracture resistance.
So it's a lot of new surfaces to create, which has a very large energy cost.
Absolutely, yeah. Hang on.
And further applications of this, Hari?
Right. So for example, here is a steel forging press or a die. And these things typically are very expensive, right? You can imagine. And you want to make thousands and millions of components. And they tend to wear out when they have impact of high temperature and this mechanical loading. So typically we have coatings, which are chrome coatings, and we want to replace them with harder materials, which can also withstand fracture. So we want to design materials and test them for those scales. These could be nitride coatings and so on. Do you probably want to explain how you do this? James?
Yeah, so I mean, we need to use these small scale mechanics because we have very thin coatings. And as was shown for the copper before, is that the properties can change based on the size of your material system. So in this particular case, we looked at these hard ceramic coatings. We studied the fracture behavior using a technique called micropillar splitting. And we did this at a range of temperatures to kind of simulate the real life conditions that these protective coatings would undergo. What we see here is that when we look at the fracture toughness, as Hari explained, against temperature, so we see for a lot of these ceramic coatings an increase of the fracture toughness with temperature. And so now I think you've developed a little bit of an understanding is that we can dissipate energy through plasticity, so dislocation movement through a material, and that these barriers for dislocation movement are also thermally activated. So if we increase the temperature, then we make it easier to move dislocations along those slip systems. And so in effect, that's what we see here, is that at increased temperatures, we're able to get more and more dislocation plasticity through the material. And this leads to a toughening type approach, so we're able to dissipate some of that energy at the crack tip. And this is really nicely related to Hari's last slide on the seashells, is that we can then take these mechanical properties, we can put them into a model so that we can create also these architecture type multi-layer coatings. So we put a number of interfaces within the system. And this leads actually to really much stronger coatings which outperform the current state of the arts for steel forging dies.
Right. To add to what James said, this interface sort of engineering is also useful in this. What you can see is a silicon carbide aero engine. And these are also useful when you want to engineer ceramic interfaces. When they start behaving as though they're metals, you start dissipating energy so that you do get this tough response. And one of the things that is relevant here is we want to have coatings which can protect these silicon carbide at elevated temperature, where it is specially susceptible to water vapor corrosion. So we want coatings which is resistant, is a combination of temperature, water vapor, and aggressive media. So things like these, the tests that you nicely showed, are useful to quantify whether these things can put up to that extreme condition. So me and James have been talking quite a bit about strength and fracture dependence of materials. The question is it enough? Clearly, Wolverine is strong and his material, adamantium, is indestructible. But some of you know that when Magneto comes in, he can easily just manipulate him and keep him at bay. Now, increasingly in engineering situations, we can think of circumstances where things like electric fields, magnetic fields become very important when it comes to application. So I can think of a couple of examples, like many of these are phone computer chips and so on. We have these, like James pointed out, we have copper at a very fine scale, and which carries current. So the electric field influences properties there. So the mechanical properties essentially really take a back seat, and functionality becomes much more important. This is also the case, for example, with say superconducting coils for when you want to move maglev trains and so on. So these things are going to carry a huge amount of current and huge amount of electric and magnetic field. Your material functionality becomes much more important, and mechanical properties are only important that they keep the system in place and the things don't break apart, right? So maybe you want to explain that, James? And
Sure. Yeah, I mean, it's a perfect opportunity to kind of end the talk and to talk a little bit about then the outlook of materials, where we're, as Hari says, we're not really so heavily focused on designing. Of course, we need to keep this in mind, but we look towards functionality. So we want to have materials which also have some particular function. And one really nice application of these, there are two that I'll just describe briefly, is for space exploration. So if you think about functional properties that one would need for space exploration, of course, materials need to be lightweight to conserve fuel, that we need to have protective coatings because we have a lot of radiation from the sun, that we might need to have specific optical properties or magnetic properties or electrical properties as well. And so there's some really nice recent work that has been looking at flexible optical solar reflectors, which touches upon a lot of those points where we need to understand actually at small length scales fatigue and fracture of materials. Of course, when we send things out into the open space, we also have extreme conditions. This might mean cryogenic temperatures, it might mean extreme high temperatures. And so, of course, we need to understand stress strain diagrams and fracture at those extreme conditions. And finally, some of the work that I'm now kind of working on with the German Aerospace Center is looking at granular materials. So things like 3D printing in microgravity environments and the effect that this has on the properties of materials. So these are some nice applications of different gear parts of amorphous glasses, so amorphous alloys, which can withstand cryogenic environments which are 3D printed. The second outlook, which is really important to society and where I think also small-scale mechanics will play an increasingly important role in the future, is energy systems. So as we discussed very briefly, we have protective coatings, so high temperature coatings that we might have for engines or turbines. We have maybe materials for fusion reactors that might become increasingly important in the future. We have battery materials, so for lithium-ion batteries or future sodium-ion batteries, including at solid state. We have, due to the intercalation of these ions during battery operation, a lot of straining, so fatigue-type straining of our battery systems, and mechanical reliability is really linked to these small-scale type fatiguing and straining of the material. But also, hydrogen storage is really a critical issue in terms of energy systems. This picture here is of a train that was developed recently in Germany, which runs off a hydrogen fuel cell type system. One of the critical questions that we need to answer is to design in terms of mechanical safety. So hydrogen can embrittle materials, and we have a group here in the department run by Dr. Yasmin Duarte that actually focuses on this question of how hydrogen interacts with materials and can influence its strength and plasticity and fracture, as we've outlined in the talk today. So to just end, just to give, as I leave this slide up here, a synopsis of the group. I mean, we're really focused on techniques, so developing fib-based techniques, in situ instrumented nanoindentation-based techniques, so that we can probe materials on very small length scales. And we connect this to materials and also processing technologies. So materials might be things like advanced alloys or steels, ceramics, as Hari said as well. And then we also link this, of course, to advanced processing methods like additive manufacturing or thin film deposition. And so to end on that note, I just want to really stress actually here that nano and micromechanics is a really crucial tool when we want to understand materials on small length scales and to be able to then design materials on small length scales, which is of course becoming increasingly important in today's world. That we can also use these techniques to analyze deformation mechanisms. So in terms of plasticity and also fracture, we can really dig into the fundamental mechanisms which affect that sort of failure and deformation. We can also use things like high or low temperatures to probe a little bit in terms of those mechanisms, because many of them are thermally activated, and we can try to understand that in greater detail. And that if adamantium, if this was existing in real life, that probably wouldn't be as great as it looks in the movies, that we would have some sort of physical limitation based on the theoretical lattice strength, as we discussed. And that also in real materials we have defects. And this influences then the plasticity and fracture of materials. So Wolverine might be in a little bit of a trouble unless he discussed with a materials scientist beforehand. So on that note, we take any of your questions, and would like to say, I mean, for people interested in visiting during their master's or PhD, that these sort of techniques can be really complementary to material scientists who are trying to understand their materials in great depth and detail. So thank you very much.